Hello, in this video we will see the figure that the circuit that we get in the differential amplifier with the current mirror as a load, that is active current mirror. So when we calculate the gain, in that gain we get the, so let me tell you the very fast way what does it required. So this is simply, if you see the diff amp, V in by 2 minus V in by 2, this is V out, single ended out. So we want single ended output and differential input. Okay, so that will be the gain and that will be the AV. So we want this, and for this the method is to short circuit transconductance multiplied by the R out. So that will be looked from here. So in short circuit transconductance the circuit will become like this. So this will be the something like this, and this V in by 2, and this will be short circuit and short circuit current, and this minus V in by 2, and this will be this. So this is the figure of interest. So the question is this circuit symmetric? First, or second is what is the voltage Vp. Okay, so this is what we want to see here. So question is this circuit symmetric? So answer is no, because this potential is not equal to 0, that is these two potentials are not same, so this circuit cannot be symmetric. Now to calculate Vp, let's go in the approximation. Okay, so in approximation, if you see closely, so this is 1 by gm. Please visit previous videos that how it is 1 by gm. So this is 1 by gm, and since it is short circuit ground, so this is ground. Okay, and this is V in by 2, this is minus V in by 2. So what is the potential here? So let's say this is Ix and this is Vx and this is V in. So what I want is, let's say I change the Vg to delta Vg, some small change in the Vg, and I want to see what is the delta Vx here. So if you calculate here, delta Vx is delta Ix multiplied by R equivalent at this node. So R equivalent is 1 by gm, and looking from here it will be R naught 1 plus gm1 multiplied by the equivalent resistance from here, and it is 1 by gm2. This is 2, this is 1. Please visit previous video how it is 1 by gm2. So it will be is 1 by gm2. So this will be the R from here, and this is 1 by gm here, and the total is 1 by gm2. So this is approximated, and the approximated value is this. And if you see closely, that delta Vx is very small, so it is small, and in the approximation we can say it is 0. Okay, just in the approximation, not the actual value. In the approximation we are saying it is 0. So if this voltage is 0, and this was also 0 because of the short circuit current requirement, and this is V in by 2 and this is minus V in by 2. So if you elaborate this circuit, what we see is this is GMVGS, this is GMVGS, and both the currents are same. Hence this potential will be 0. How it is 0? So let's see okay, let's see here. So let's say this is 2 ampere and this is 2 ampere. Okay, previous means t minus. Okay, this 2 ampere, it is 2 ampere. This resistance, across resistance are 1 ampere current going. I'm just explaining in term of example. So at t equal to 0 positive, let's say when there is a delta input change, so what will happen? Let's say this current will be increased to 3 ampere. Okay, and if you see here, this current also increased to 3 ampere. Because of the input delta input change, we see this delta current change, and that current increased value is 3 ampere. So this current will go 3 ampere here total. Okay, and initially it was 2 ampere. Okay, now let's see the resistance current. So earlier it was 1 ampere. So what is the value here? What is the value of the voltage here? So this will be, I'm explaining in term of previous state. In previous when before changing the current, before changing the input gate voltage, let's say for example the current through this is 1 ampere and this is R. Let's say R is equal to 1 and this is 1 ampere. So this voltage will be 1 volt. Okay, now after increased in the current both side, we don't see any change in the current here. Okay, here also there is no change in the current from this terminal. So because of this, there is no change in the current, and this voltage is 0 volt. So this voltage is 1 volt again. So initially it was 1 volt and again it is 1 volt. So delta, let's say this is Vp, delta Vp is 0. Okay, so this is the way of seeing the circuit, that when this potential, you see this potential is 0 and this potential is also 0, same potential 0 0, and the current is same here. So there is the extra current, which was coming from here is going all here, and there is 0 voltage here. So this, in this specific circuit, if you see, so because of approximation, we can make this delta V 0. Because of the approximation we make 0, and from here we can see that this potential is delta change in the voltage is 0. So hence we can say that the change in this Vs or Vp is 0. Okay, so we can say from here that this potential Vp in AC means delta Vp is 0. Okay, change in the potential is 0. So whenever you draw the AC equivalent circuit, this potential will be equivalent to 0 in approximation, not exact. Okay, so in the approximation we see that this is 0 volt, and the reason for this 0 volt is that Vp is 0. Because of this here it came 0, the gain, the R equivalent 0, and this voltage is 0, and because of this voltage 0, here I explained clearly that the extra current that is generated here will directly go here. Okay, the extra current, which comes here will directly go here. Okay, there is no current change here, delta I current change in this branch, in the resistance. Okay, there is no change in the current in the resistance. Let me share with you in detail. So this, and this. So whatever delta I change here will go here. Okay, and this voltage is 0. So I am explaining in this for this specific circuit only when this potential is 0. Okay, so in this specific circuit when this is 0. Okay, why this is 0? Because here delta Vx is 0 and here the short circuit made for the short circuit current. So when this is 0 in both the cases, 0 volt and 0 volt, and whatever delta I current comes, it will go here. Okay, so there is no delta I R, so there is no current change in this branch. So whatever delta V voltage, because of what is delta V? Delta V is delta IR multiplied by R. Okay, so there is no current change. Why? Because whatever change in the current happens, it will go this way and no current will be available for this branch, no delta current. Okay, so because of that delta V is 0. So we can say that this potential will be 0 in AC analysis. Okay, so this is one of the point that this potential is ground, virtual ground, and important point is look at the circuit, how the circuit looks like for this case only when there is a short circuit here. Okay, and this potential becomes 0 volt and this potential will become nearly to 0 volt delta V because of the input change. Then only we can say that this is 0 volt, Vp is 0 volt, and that is only in the approximation this is 0 volt. Okay, so you have to see the circuit also. You can't say that every time it is for example, let's say this is this circuit. Okay, so in AC plus V in by 2 minus V in by 2, this is V1, this is V2. Okay, so and this is diode connected. So is this circuit symmetric? Obviously no. Okay, so you have to see the circuit and Vp point, that how to see that what is the value of this potential. So in this specific circuit where this potential becomes 0 volt, then only and this potential is small and we considered it, we approximated it to 0, then this Vp becomes 0 volt and then we have approximated it to 0 volt. Okay, now we will see another video where we will calculate complete GM value and complete R out value. In this we will only see the potential at this node is 0 and this is unsymmetric circuit. Another point that I want to share with you, just so if you see here closely, this is the circuit from short circuit transconductance calculation. So what is the voltage here? What is the equivalent circuit here? From here if you see, look, so equivalent circuit is, I am talking about the equivalent circuit, not equivalent resistance. So there is a difference between equivalent circuit and equivalent resistance. So if you calculate the equivalent resistance, then it is 1 by GM2. Okay, but in that case you have not included the V in whatever the voltage available here. So in that case we have to see the equivalent voltage and equal Thevenin voltage also. Okay, so we know that we can make let's say this circuit is this and this is RL load. So we can assume this circuit as R Thevenin and V Thevenin. V Thevenin is open circuit voltage from this node and this is RL. So this was the basic. So here also if you see from here you can see the R equivalent is 1 by GM, but for equivalent circuit you need to have the Thevenin voltage also, that is the open circuit voltage, and I have mentioned here open circuited here and calculated the Thevenin voltage. So if you calculate the Thevenin voltage, so it will come like this GM R naught. So it will come something like this. Thevenin voltage is open circuit voltage and it will come like this, that GM R naught 1 plus GM BG. Okay, so coming to the problem, that this circuit is equivalent to 1 by GM and the voltage, Thevenin voltage, that value is this. Okay, so this circuit will not be equal to this circuit. It will be equal to 1 by GM, and the equivalent circuit we have include the this voltage also. So this is the equivalent circuit. Okay, note that when we do the superposition, then we make this this Vin by 2 equal to 0. In that case, when you draw the equivalent circuit, when Vin minus Vin by 2 equal to 0, in that case when you draw the circuit, then this will be correct. Okay, but if you want to include both Vin by 2 and minus Vin by 2, in that case you have to have the Thevenin voltage here. So this is the correct figure. So from here I just wanted to share that whenever you draw the circuit, so take care of these two voltages, that Vin by 2 minus Vin by 2. What is the circuit you are making? If you are making this superposition way, then there is no problem in looking to R equivalent circuit, and then you are making the circuit R equivalent. But if you are including both Vin by 2 minus Vin by 2, then you have to use the Thevenin way, VTH and RTH, and RTH is R equivalent. So this is the point here that I wanted to share. Okay, and you can see that when it is open circuit what is the Thevenin voltage and how I have added here. Okay, basically RTH and VTH. Okay, so this is the point to be looked, that how to analyze the circuit. So in this video what we saw that for calculation of differential amplifier with the current mirror as a load, we need GM, short circuit transconductance, and the circuit will become like this. And we want to know, can we apply Vp is equal to 0 here, virtual ground, can we apply? So yes, we can apply, but in approximation only, and in approximation this voltage becomes 0, and then we can make this 0. And how it becomes 0 volt? Because how this becomes Vp equal to 0? Because if you see the equivalent diagram, here, change in this current will be accommodated by this change current. Okay, change in this current will be accommodated by this current change. So the change in resistance current will be 0. Hence this voltage change will be 0. So I hope it is clear from the explanation that I shared with you. Okay, so you can go back and see in this figure that how in both these two figures, that how the change in this current will be taken by this change, and the whatever the current here present before will remain same, and that's why this voltage will become, the delta change will be 0. Only thing to be noticed here is that this voltage is 0. So please look into the video carefully and understand the basic concept of the how we can use the virtual ground concept in active current mirror load in the calculation of the short circuit transconductance. Okay, so important point is we need to look the circuit also, that is it symmetric or not, or is it what is the circuit. Then based on that only you can apply the symmetric Vp equal to 0. This was made 0, so you can see this is symmetric. Okay, so thank you.